Electromagnetism is where electricity and magnetism collide as two sides of the same coin. In this video, we'll discover how electric currents generate magnetic fields and how those magnetic fields will affect other moving charges. From Ørsted's experiments to the inner workings of a mass spectrometer, this is the fundamentals of electromagnetism. Magnetism has been studied since the ancient Greeks, who first noted that certain stones in the ground called lodestones would cause for iron objects to be attracted toward them. For this reason, we often use iron filings to study how these objects will behave when they're around a magnet. This is because iron is essentially attracted to any type of magnet. However, some magnets will attract or repel other magnets. In this way, we would say that the magnets have a north and south side. Every magnet has a north and south side, and the south is always attracted to the north, and the north is always attracted to the south of another magnet. So opposites attract again. It's like we have two different sides of a magnet, and those opposite sides will be attracted to each other. In fact, the Earth itself behaves as a giant magnet. When we put a compass needle present in the Earth's magnetic field, the compass will be deflected according to that magnetism. So in reality, the North Pole, the geographic North Pole of the Earth, is actually the magnetic South Pole of that object, because the north end of our compass is attracted to the south magnetic pole of Earth. We would say that a magnet generates a magnetic field everywhere around it that influences other magnets or moving charges when they're brought into that magnetic field. This is a lot like an electric field, which can influence other electric charges without actually directly contacting them. The variable for the magnetic field is the letter B, and it is a vector, meaning that this magnetic field has direction at different points in space. The SI unit for the magnetic field is a new unit called the Tesla. And similar to the rules that we had for electric fields, there are also rules for magnetic field lines that we could draw around the magnet. The magnetic field lines always exit out of the north end, pointing out from north, and the magnetic field lines always return back into the south end of the magnet. In this way, it's sort of like our south end is a little bit like a negative charge and our north end is a positive charge, but really this is a different phenomenon. So you'd rather think about it as basically being north and south, and there will always be a north and south end of a magnet, and the magnetic field points according to those directions. If we were to continue these magnetic field lines and draw them everywhere around the magnet, we would see that we could connect these into a continuous line that only within the magnet itself points from south to north, and everywhere else the magnetic field lines leave the north end of a magnet and enter back into the south end. In this way, we would see that magnetic field lines never cross, and that the strength of the magnetic field at some region in space is essentially based on how close together the lines are in that region of space. How many magnetic field lines are there in a given area of space? That will dictate the magnitude of the magnetic field at that location. And remember, just like the electric field was a vector and it could add together with other electric fields to either cancel out or become larger, the magnetic field is also a vector. So we're going to need our vector addition rules. Remember, if a magnetic field points to the right and then there's another field that points to the left, those two would cancel each other out because they have opposite components in that direction. So you'll need to use trigonometry, triangles, and all of the understandings that we have about vector addition up to this point to calculate the magnetic field for multiple magnetic fields in a region of space. For example, you would see here in this example B, if we have two magnets near each other with the north end facing the south end, the magnetic fields from the left magnet would point out of the north end, and the magnetic field from the right magnet would point into the south end. And so both of those separate magnets would have two magnetic fields, and those would add together to be the total in the middle, which ends up being a larger magnetic field between these two. On the other hand, if we were to have two north ends facing each other, like you see in part C, these would both have a magnetic field leaving, going out of the north end, one pointing right, one pointing left. And so right in the center, the components from both of these magnetic fields would cancel perfectly. And right between these two, we would get a total magnetic field of 0. Now, it's easy to talk about magnets based on like refrigerator magnets, because that's what we've seen in our real life. but actually magnetism occurs in some other places rather than just in certain stones and objects. In 1820, Hans Ørsted was doing a lecture demonstration, just like another lecturer that you know, and he noticed that when passing electric current through a wire, that a compass needle on the wall deflected. Could it be possible that electricity flowing through a circuit can cause magnetism? Ørsted got to work and began studying how currents flowing through wires can create magnetic fields, and he studied this by using iron filings. Here we see that Ørsted initially is just placing iron filings around a standard bar magnet and tracing out the way that the iron filings fall, creating the magnetic field. But when he puts these iron filings near a wire and runs a current through them, they seem to behave differently, as if they're surrounding the wire in a circular pattern. And Ørsted began to think that the magnetic field could be some type of field that goes around a moving charge. Electromagnetism is the study of how moving charges can generate magnetic fields. And keep in mind, when I say a moving charge, that's a lot like an electric current. So these two are somewhat synonymous in terms of electromagnetism. But the way this works is essentially if we hook up some wires to a circuit and create them in a certain geometry, when we turn on that circuit, all of a sudden it will become magnetic and objects will become attracted to it. So if we try to map out the magnetic field of a coil with current running through it, we see that it behaves a lot like a bar magnet would, causing for iron filings to sort of splay out on each side of the end of the coil, and within the coil, all of the iron filings align as if there's some type of magnetic field putting them into place. So every time we have a moving charge, every time we have an electric current, there is also a magnetic field that is generated around that current. For example, if we were to run current through some type of loop, a wire that's bent into a circle, we would find that the compass around this loop would end up being deflected in different directions. That looks a lot like what you see here. There's a magnetic field generated around this current loop that points upward from the face of it and downward, outward from the bottom of it. In a similar sense, if I was to unbend that current loop and just run current through a straight wire, we could even find that a compass needle is deflected around that straight wire with a current flowing. The compass needle rotates as if its direction is in a circular pattern around a straight current running through a wire. If I imagine that wire as being like a straight up and down current directly in the plane of the page, we could see that we can map out this magnetic field. And on the left side of that wire, essentially the magnetic field is always pointing outward, out of the page toward you. And on the right side, the magnetic field is always pointing inward, away from you, into the screen. And so we will need to be able to think in 3 dimensions to discuss magnetic fields. If we're thinking in 3 dimensions, we will need a 3D coordinate axis, each with 3 variables to represent those different dimensions. We'll use X to represent right and left motion, with rightward being positive conventionally, Y to represent up and down motion, with up being positive conventionally, and we introduce a new variable called Z, a new dimension, which now has a positive and negative direction, and Z describes the position out of the page as being positive toward you, and into the page away from you as being negative. You can sort of see that in this diagram right here of this coordinate axis being rotated. You'll see that if we try to sort of visualize those Z-axis, it's coming out toward you in the positive direction and away from you in the negative direction. And we can sort of imagine spatially translating that in our mind and imagining it. Sometimes we would say that there is now 3 sets of planes that intersect with each other. This blue plane, that would be the XY plane. The green plane would be the ZY plane, and the orange plane would be the XZ plane. So now instead of just having X and Y, we now have X, Y, and Z. That means positive X is to the right, negative X is to the left, positive Y is upward, negative Y is downward, and positive Z we would say is out of the page, and negative Z we would say is into the page conventionally. So for almost all these problems, you'll want to start off by drawing your standard coordinate axis in X and Y, but really now there's like a third dimension. It's kind of hard to draw in a two-dimensional surface, but this third dimension has a negative Z that goes backward and a positive Z that goes forward out of the page. And since we're trying to draw these on 2D surfaces, instead we will use these vector symbols to represent the direction of positive and negative Z. If we want to represent a direction in the positive Z-axis, we will use this circle with a dot in it, as if it's an arrow coming out at you, and you're seeing that dot as the tip of the arrow, and the base of the arrow is sort of being the circle around it. This would be the positive Z direction. Oftentimes we would say that this is also counterclockwise, sometimes is what will be said for this. And this symbol with an X in it represents the negative Z-axis, or the negative Z direction. We would say that this is like looking at the back of an arrowhead that has an X on its bottom. And we would also say that the negative Z direction sometimes can be considered the clockwise direction. Now that we know how to think in 3 dimensions, we can use the right-hand rule to determine the direction of the magnetic field coming from a current-carrying wire. There's 2 right-hand rules, and the first one is called the grab and curl method, and the instructions are listed below. Essentially, if we have a wire carrying a current, you will want to first grab the wire with your right hand. Put your left hand behind your back every time you need to do one of these. All coordinate systems are right-handed, so you'll grab the wire with your right hand, pointing your thumb in the direction of the current. So for this wire, our current is going out in that direction. And then you will curl your fingers in the direction of the magnetic field all the way around that wire. So let's take a look at an example. Imagine that we have a current carrying wire with the current flowing in the positive Y direction. We would get out our right hand and grab onto that wire with our thumb pointing in the direction of the current. And as we loop our fingers around in a circular pattern, as we curl them around, we will see the magnetic field direction anywhere around that wire. So let's consider it as this wire right here. We'll grab it with our right hand, and you will see that our fingers are pointed outward everywhere on the left side of this wire, and that our fingers will curl inward everywhere on the right side of this wire. So that means that the magnetic field can be drawn on the left side of the wire as a circle with a dot in it. That's what this solid dot means. Sometimes people will just draw it as a solid dot, but this circle with a dot in it, that is the magnetic field generated on the left side. And the magnetic field generated on the right side would be inward. So we would use a symbol with an X surrounded by a circle. That's the magnetic field generated by the wire on the right side. And technically, anywhere in front of the wire the magnetic field would point in a different direction. It would point rightward in front of the wire, if we could somehow draw that, and it would point leftward behind the wire. So it's like these magnetic field lines are curling around in front and then behind, curling back around behind that wire to the left. In this way, we can draw the magnetic field lines around a current-carrying wire as concentric circles, with them being closest as we are near the wire, and the magnetic field lines get spread out farther apart as we get farther away from the wire. So here's some practice examples for right-hand rule number 1. I'll help you with the first one, and then I encourage you to pause and try the next ones yourself. Let's imagine current is flowing in the negative Y direction. We would grab onto that wire with our right hand, having our thumb pointing down. So get your right hand out, put it in line with your computer screen, and point your thumb down, and you will find that your fingers curl away from you. On the left side, that would be in the negative Z direction. And so everywhere along the left side of this wire, we would have a magnetic field from that wire that points inward, and then our fingers will be tracing a path outward on the right side, and so the magnetic field from that wire everywhere around it would be in the positive Z direction. So here's 4 more examples for you to practice on your own. I've drawn in the hands a little bit to help you kind of get used to things. Go ahead and pause the video and see if you can figure out the direction on either side of the wire within the plane of the page. Using the right-hand rule, we would see that our magnetic field from our wire points outward everywhere above this one and inward everywhere below it. We would find that our magnetic field points inward everywhere above it for this next example. And then our magnetic field points outward everywhere below it. Our fingers are heading out of the page below that wire. And then for these examples, we have our current flowing in the positive Z and negative Z direction. That's like drawing a wire that's coming out toward you or into the page away from you. So for this one, we would grab onto it with our right hand and we would show that the magnetic field is in a circular pattern that our fingers would trace around that. It's like our magnetic field is a circular pattern everywhere around that wire within the plane of the page. And for the other one where the current is going in, we would see that our fingers would curl in the opposite direction. So our magnetic field everywhere around this wire would follow this circular path. We can calculate the magnetic field generated by a long straight wire with a current running through it. We approximate a wire as being infinitely long because that would make the whole situation symmetrical for the entire region of space that we were looking at. Of course, this is a little bit of an approximation, but if we assume that the wire is infinitely long, this would be the case for if we were like close to the wire, a distance that was much less than the actual length of the wire. We could calculate the magnetic field generated by that wire depending on the current going through the wire and depending on how far away we are from that wire, a radial distance away from any position on that wire. And it also, in this equation, features mu0, which is called the permeability of free space. This is a constant of our universe, and it is equal to 4 pi times 10 to the minus 7 in its standard units. So we would see that as the distance increases, as we get farther away from this wire, the magnetic field lines are farther spread apart, and that means that the magnetic field strength is lesser. Previously, I said that magnetic fields are vectors, which means they obey vector addition. If I have two different magnetic fields in the same region of space, I need to use vector addition to figure out the total magnetic field at that location. For example, if we were asked to find the total magnetic field from two wires at some point of interest P, we could calculate that by using the long straight wire magnetic field equation. If we assume that each current running through these wires is 1 amp and 2 amp respectively, and that we're looking at some position of interest at a location of 2, 4 measured in centimeters, we can calculate the magnetic field from each of these wires and add them together. That means that I'll want to calculate the magnetic field generated from wire 1 and the magnetic field generated from wire 2, thinking about what direction they point in, and then add those together to find the net magnetic field vector. And now that I have the magnitude of these two magnetic fields, let's think about what direction they would actually point in. Current 1, if we use the right hand rule, will have a magnetic field that points out of the page above the wire at this location of interest. So we would say that B1 points in the positive Z hat direction. On the other hand, current 2, if we use the right hand rule, that would be pointing into the page at that location of interest in the negative Z hat direction. And so these two are in opposite directions. When I add together B1 plus B2, we're going to need to think about them in the Z hat direction, in the Z in or out of the page, and how they'll add together. We have positive 5 times 10 to the minus 6 Tesla for B1, and then we have negative 2 times 10 to the negative 5 Tesla for B2. And so when we add those together, we will see that we end up getting negative 1.5 times 10 to the minus 5 in the Z hat direction. That means that overall, the net magnetic field from both of these wires added together will have a strength of negative 1.5 times 10 to the minus 5 Tesla in the Z hat direction. That's into the page away from you. And as one final tip, remember the distance of both of these wires to the point of interest R1 and R2 are different variables. R2 would essentially be the x distance from that wire because it's going up and down. The radial distance away from that would be in the x direction, whereas R1, the distance from the first wire, would be a radial direction upward away from that horizontal wire. So if moving charges and electric current running through a wire creates a magnetic field, that magnetic field can influence other magnets or other electric currents that are brought into that magnetic field. In this way, we can calculate a force between two current-carrying wires. The force between two current-carrying wires can be calculated with this equation in pink, where mu0 is, of course, the permeability of free space. I1 is the current through the first wire. I2 is the current through the second wire. L is some length along the wire that is feeling the force, and R is the distance that separates the two wires. When we do out the math here, we would see that these two wires will actually end up attracting toward each other if their current runs in the same parallel direction. It's like the magnetic field from the first wire is influencing the current in the second wire. And the opposite would hold true for currents running in the opposite direction. Those two wires would repel from each other. We would see that the force between the two wires will end up being repulsive if the currents are in opposite directions. One's going into the page, one's going out of the page from this bird's eye view. Whereas if the two currents are going in the same direction, both out of the page in this bird's eye view, the attractive force will bring these two wires together. That's the magnetic force. In general, the magnetic force on a current-carrying conductor can be calculated as a cross product between the current, the length of the segment that is carrying that current, and the magnetic field that it is present in. Remember, L is just some length of the wire that is feeling the force. It's measured in meters, and so since these are infinitely long wires, I need to pick just some chunk of that wire to look at, some unit length. Maybe it's like 1 meter of the wire. How much force does a meter of the wire feel? And so that's what you might plug in for L. Now, this is a vector cross product. This is what happens when we multiply together two vectors like you see here. I times L is one vector and B is another vector, the magnetic field. For a cross product, we can always calculate the magnitude of this cross product as being the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. If we have a 90-degree angle between these two vectors, then this equation would be maximized and the magnitude would just be IL times B. But determining the direction of this magnetic force involves another right-hand rule. Before I get into that more specifically, let's just talk a little bit more about that cross product. Really, there are two ways of multiplying vectors together in physics class. We haven't talked about this too much, but now it's important to get the details out of the way. If we have two vectors that are being multiplied, we could take a dot product between those two vectors, which would return a scalar answer. And the way the dot product looks is essentially if I have two vectors with a dot symbol between them, I can calculate the magnitude of that vector as being the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between those two. And one place where you may have seen a dot product is actually in calculating the work, which is the force dotted with the distance. You know that this work equation eventually becomes FD cosine theta. In truth, that's what's going on with the work equation. But we could also multiply our vectors together using a cross product, which is a mathematical technique that would return a resultant vector, not a scalar, but a vector that has its own direction and magnitude. The magnitude of a vector cross product can be calculated by taking our two individual vectors with a time symbol in between them, that means a cross product, and the magnitude of this would be the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between those two. Some places where you may have seen a cross product is in calculating the magnetic force on a current carrying wire, IL cross B. But another place where you may have seen the cross product is in the torque equation, where the torque is actually an R vector crossed with a force vector. Eventually, the value of the torque can be said to be equal to RF sine theta. So that's really where this equation is coming from. Right-hand rule number 2 is called the pointing palm method, and this can be used to solve for the direction of any vector cross product. For now, we'll just focus on the magnetic force, which is FB is equal to I times the cross product between L cross B. And so that'll be our example, but this would work for any other cross product as well. Step number 1, you will want to point your thumb in the direction of the first vector. In this case, that's the current IL vector. L is a length that runs along the direction of the current. Then you will point all of your fingers in the direction of the second vector. In this case, that would be the magnetic field at that point in space. And finally, you will keep all of your fingers together and your thumb flat so that your palm, depending on how you rotate it, your palm will open up in the direction of the resultant vector. So let's give this an example. If we have current flowing in the positive X direction, like you see in this diagram, present in an external magnetic field that points into the page away from you, then you'll want to get out your right hand and use your right hand rule to have your thumb point in the direction of the current, your fingers point away from you, and you would see that your palm faces up in this case, like you see in the diagram. You point your thumb to the right, that's in the direction of the current, the first vector. You point your fingers all together away from you in the negative Z hat direction, that's in the direction of the external magnetic field. And whatever way your palm points when you're doing this motion will be the direction that the magnetic force is, the resultant vector. So if we're looking at the magnetic force acting on a current carrying wire, we can use right hand rule number 2 to determine the direction of the magnetic force acting on these currents. For example, in part A, if you were to point your thumb down of your right hand and your fingers out of the page toward you, get out your right hand, point your thumb down, point your right hand out of the page toward you, and you would see in this case that your right hand will face in a direction that gives you the resultant vector for the magnetic force. So for this first one, we would find that the magnetic force acting on this wire pulls the wire to the left. I don't quite know how big that number is until I do the math, but at least I know the direction. According to right hand rule number 2, it'll point to the left on this current. Go ahead and pause the video and try the rest on your own before we display the solutions. So here, when we take a look at these solutions, did you get them all correct? Part B would have a magnetic field that points into the page, the negative Z-axis. Part C would have a magnetic force that points upward in the positive Y direction by our right-hand rule. Example D does not actually yield any value for the magnetic force. If the current is 180 degrees with respect to the magnetic field, then the magnetic force would equal 0 in our calculation of its magnitude. So there's no magnetic force in this case. For part E, the magnetic force points to the right in the positive X direction, and for part F, the magnetic force points down in the negative Y direction. In reality, the infinitely long wire is not necessarily the best approximation, especially when we are very far away from a current carrying wire. If we get really far away, that infinitely long wire would start to feel smaller and smaller until we could approximate it as a short wire. And the magnetic field from a short wire has a slightly different equation for calculating it. Here is the magnetic field coming from a short wire, where of course I is the current, L is the length of the wire that generates that magnetic field, R is a radial distance away from that short wire, and phi is an angle that measures the angle between the current that is generating that magnetic field and the point of interest in space at a distance r away. Now, straight wires are a great way to start by studying magnetic fields, but in truth, to get a very uniform and consistent magnetic field, we're going to take that wire, and instead of it being a straight line, we're going to bend it into a circle. Using our right hand rule, we'll see that this also generates a magnetic field, and we can figure out the direction of that magnetic field generated by a circular current carrying loop. The magnetic field at the center of the loop can be calculated with the equation that you see here. And the direction of that magnetic field still follows the right-hand rule. If I was to grab onto the front of this circular loop with my right hand, we would find that my magnetic field would be upward anywhere inside the loop, and anywhere outside of the loop over somewhere around here, my fingers would be curling downward. So really what we care about is the magnetic field inside of this loop, because everywhere around that, whether I grab the front with my right hand or the right with my right hand or the back with my right hand, my fingers will always curl in the same direction to give a total magnetic field at the center that is nearly uniform. All of these magnetic field lines are about the same distance apart, and so our circular current loop is a way of generating a uniform magnetic field at the center of the loop. Now, the magnetic field begins to diverge as we get farther from the center of the loop, so we could also calculate the magnetic field produced above a current carrying loop, and we would call that B, above the loop. And so you would use this equation, which is significantly more complicated than the previous one. But let's just take a minute here. We have μ0, we know that's a constant. I is the current running through that loop. Capital R is the radius of the loop itself, and Z is the distance that we end up calling this vertical distance above the center of the loop. The farther away that we get, the smaller that magnetic field would be calculated as, and the closer we get to the center of the loop, that would be like when Z is approaching 0. As we get closer to the center of that loop, this equation collapses down to the one that you saw on the previous slide for the magnetic field at the center of a current loop. So here we are inspecting an example of two single current carrying loops, each carrying a current of 10 milliamps, each with a radius of 50 centimeters. We're asked to calculate the magnetic field at a point P halfway between those two if they're separated by a distance of 1 meter. So the total distance separating these two is 1 meter, and that means the distance from one loop to my point of interest P is just 0.5 meters. It's like we're 0.5 meters above the first loop and 0.5 meters below the second loop. So we'll go ahead and find our equation of B above some current loop. And let's just start by calculating it for the first loop. That's the one on the left. In this case, I will use an X to represent that Z variable, because really the offset distance from the center of the loop is in the rightward direction for this first loop on the left. And so we'll use X to denote that distance from the center of the loop. And so for this calculation, I end up getting 4.44 times 10 to the minus 9 Tesla. And the direction that this would point would be according to the right hand rule. So I would have to grab onto this current loop with my right hand, and I would ask myself, what way would the current point if I was to grab it with my right hand? That would have a magnetic field that goes in from the right side and goes outward from the left side everywhere throughout that loop. And so what our magnetic field might look like from that first loop could be something like that. In other words, our first loop has a magnetic field that points to the left in the negative x hat direction. Now we can calculate that again for our second loop. But we would find that each of these variables is basically the same. The distance from the center of the loop, of the right loop, is going to end up being 0.5 meters, and it's to the left for this one. However, since that value is squared, we're actually going to end up getting the same exact number for this second current loop. It also generates a magnetic field of the same strength, since they're equidistant from that point, and that magnetic field for this loop would also, since its current is facing in the same way, point to the left everywhere through that loop. And so this one also points in the negative x hat direction. And so to figure out the total of both of these added together, the net magnetic field would be B1 plus B2. And in this case, we would see that we end up getting a value of 8.88 times 10 to the minus 9 Tesla in total, all pointing in the negative x hat direction. So if a single current carrying loop will generate its own magnetic field, then what happens if we stack many current carrying loops on top of one another? Their magnetic fields will add together. And we call this type of device a solenoid, which creates its own magnetic field that's very consistent within the coil itself. Many current loops end up looking basically like a coil with current loops stacked on top of one another. And we can calculate the magnetic field from a solenoid in its center by using this equation here, where mu0 is the permeability of free space, n is the number of turns in that coil, and L is the length of the coil. And I, of course, is the current running through that coil. Inside of this solenoid, we could use the right hand rule to determine the direction. If we grab onto the front end of this solenoid with our right hand, we would find that our fingers end up pointing to the left within the center of this solenoid. And we would also find that within the solenoid itself, that the magnetic field is very consistent. It's practically uniform. And so outside of the solenoid, we would say that the magnetic field generated by it is essentially zero, but the magnetic field is maximized in the center of a solenoid, and it is uniform. So those were all different arrangements of current carrying wires and how they generate a magnetic field. But a current is just a motion of charges, a motion of positive charges. So if I could take apart that current and just think about one positive charge, even a single point charge would experience a magnetic force when it was present in an external magnetic field. And that point charge must be moving. That's what current is. It's a motion of charges. So moving charges create magnetic fields. And magnetic fields exert forces on other moving charges. Whether this is a current or just a single point charge, it doesn't matter. The magnetic force still acts. And the magnetic force acting on a single moving point charge can be calculated as QV cross B. This is another cross product between the velocity that the charged particle is moving at and the external magnetic field that it is present in. By our rules for a vector cross product, we know that we can calculate the magnitude of that resultant vector as being QVB sine theta, just thinking about their magnitudes, and the direction of a vector cross product needs to be determined using right-hand rule number 2, the palm pointing method. So go ahead and try for yourself to see if you can use the right-hand rule correctly for these 6 examples. Remember, you will want your thumb in the direction of the first vector. You will want all of your fingers in the direction of the second vector, and you will want to think about where your palm faces to determine the direction of the resultant vector. Pause the video, give all 6 a shot, and then let's see if we get the same answer. So there's our solutions for the right-hand rule. Hopefully you're getting it. Here we have an electron. That means the charge is going to be negative in this equation, and it's moving with a velocity of negative 10 meters per second. That's to the left in the negative x hat direction in an external magnetic field of 4 Teslas pointing upward. So we've drawn our diagram here. Let's determine the direction of the magnetic force and the strength of that magnetic force acting on this charged particle given these conditions. We're going to want to use our equation for the magnetic force acting on a moving point charge. And don't forget that this Q is not the absolute value. That means that our negative direction or our negative charge might end up changing around something in the end for our right-hand rule. Let's take a look. To calculate the magnitude, we would just take Q times the magnitude of V times the magnitude of B times the sine of the angle between them. In this case, our angle between V and B is a 90-degree angle. And so we end up getting an answer of 6.4 times 10 to the negative 18. That's the magnitude, but it doesn't actually tell us the direction. We need to use the right hand rule to determine the direction. So we would point our thumb in the direction of the first vector. It points to the left. However, since this is negatively charged, we're going to have to reverse this in the end. I like to do this in the first stage since it's sort of like Q and V are being multiplied together. So when our thumb was initially pointing to the left, we will now point it to the right. And then you will point your fingers upward and you'll see that your hand ends up facing outward toward you. Your palm is facing toward you in the positive Z direction, out toward you. And so when we put our thumb to the right and our fingers upward, we would see that our palm points in the positive Z direction. And so we now have a final solution for our magnetic force. We have the magnitude and we have the direction, and that's all that we can solve for. The fact that the magnetic force is perpendicular to the direction of motion gives a very unique situation which causes for a charged particle in a magnetic field to move with uniform circular motion. This means that the particle is just going to move in a circular path at the same constant speed the entire time, only changing its direction, not changing the magnitude of that speed. Since our right-hand rule would constantly lead to a force directed toward the center of the circle for this situation, we would have our charged particle moving in a circular path just like a tether ball that was tethered by some type of string applying tension, keeping that ball moving in a circle. For any particle that moves in a circular path, we could say that the force that is keeping it moving in that circular path can be modeled as a centripetal force. In truth, the centripetal force is not the real force. The real force that keeps this particle moving in a circle is the magnetic force, but we can model that force as being equal to an imaginary centripetal force, which always takes the form of this equation. The centripetal force is mv squared over r, where v is the speed that the particle moves in that circular path and r is the radius of that circular path. So if the particle is moving in a circular path according to a centripetal force, we can set that centripetal force model equal to the true force that is keeping this particle moving in a circle. We can say that the centripetal force is equal to the magnetic force. And then we can begin to back calculate out something called the radius of curvature of this circular motion. We can figure out the radius of this circle based on all of the other quantities in the physical situation. Basically, the mass, the speed of the particle moving in that circular path, the charge, and the magnetic field that it's present in will dictate the radius of this circular path. And we call that the radius of curvature, which is measured in meters. This radius of curvature is strictly based on just the mass and the charge of the particle. Because remember, the velocity is essentially constant for some situation. When a particle is in a magnetic field, that velocity would be set and constant. And the magnetic field would be something that we would set in our experimental setup. So these are constant values, and all that would change the radius of curvature for a different particle would be the mass of that particle and the charge of that particle. And so if this particle is moving in a circle, it will complete one lap in a certain amount of time. And we can calculate a cyclotron frequency, which tells us how many oscillations or how many circular paths are completed in every given amount of time. And that would be measured in hertz, and we could calculate that as the velocity of the particle moving in the circular path divided by 2 pi times its radius of curvature. This principle is used in a mass spectrometer device, which is a scientific piece of equipment that is very useful for a variety of applications. Specifically, this will analyze how different particles move in a circular path when present in a magnetic field, and those particles will be separated and analyzed based on their charge to mass ratio. Our mass spectrometer will always start with a velocity selector, which essentially makes sure that all the particles are moving at the same speed before they enter this magnetic field. So before the particles enter the analysis magnetic field, we would send them through a velocity selector, which essentially applies an electric field at the same time as a magnetic field. We would now have two forces acting on this charge. We would have an electric force and we would have a magnetic force acting on a charged particle as it moves through our velocity selector. And as long as the magnetic force and the electric force are equal, then this particle would experience no deflection. The electric force might lift positive charge downward in this velocity selector, but the magnetic field might push it upward. And if we just balance just the right magnetic field and electric field, then we can find a way to tune the velocity of particles as they move through this velocity selector. And that velocity would essentially be based on the strength of the electric field divided by the strength of the magnetic field. This would give us a constant velocity for particles after they leave the velocity selector. Next in the mass spectrometer, after the particles travel through the velocity selector, they will enter a magnetic field region, which analyzes the particles based on their charge to mass ratio. Since the magnetic field is constant in this field, and we already set the velocity to be a constant value for all the particles that pass through the velocity selector, then we can use the radius of curvature of each of these particles to say something about their charge to mass ratio. In this case, the radius of curvature could be calculated based on that equation that we had for the circular path in the previous slide. And since all of these particles have the same velocity, we could say something about how their energy is related to their charge to mass ratio. Lastly, we will discuss magnetic dipoles. A magnetic dipole is a magnetic system that has two poles, a north and a south end. And in fact, magnets must always exist as a dipole. There will always be a south and a north end to each magnet. No matter how many times I chop a magnet in half, it will always still maintain that dipole nature. Even if I cut a magnet down to the atomic level, I will find that even a single atom has an electron orbiting around that atom and spinning. That's a moving charge. That generates a magnetic field from even a single atom. Ultimately, this idea of magnetic dipoles is what causes for a compass needle to feel a torque to align with an external magnetic field. Whenever you bring a magnet near a compass, you would see that that compass would deflect, and that implies that the compass itself has a magnetic dipole moment. The torque on a magnetic dipole can be calculated. The torque on a magnetic dipole will be a cross product between the magnetic dipole moment mu and the external magnetic field B. So this is a lot like the electric dipole in an electric field, except now it's dealing with magnetism, a magnetic dipole in a magnetic field. Mu is the magnetic dipole moment. It essentially tells you about how strong the polarity is within that magnetic system. And this has units of amps times meters squared. Remember that the torque is ultimately a three-dimensional vector that could either rotate in the clockwise direction, negative, or the counterclockwise direction, positive. And now we know that really counterclockwise positive essentially means that the torque points in the positive z-hat direction, whereas clockwise essentially means that the torque points in the negative z-hat direction. And the potential energy of a dipole in a magnetic field can also be calculated similar to the potential energy of an electric dipole in an electric field. So for the potential energy of a magnetic dipole in an external magnetic field, it would be the dot product between those two vectors. Or we could calculate that value as being negative mu b cosine theta, where theta is the angle between the two vectors, the magnetic dipole moment mu, and the external magnetic field B. In this way, we would see that the alignment of the dipole with the external magnetic field will say something about the torque that it'll feel and something about the amount of energy stored up in that system at a given point in time when I look at it at a certain orientation. So that'll cover everything for our unit on electromagnetism. Of course, there's a lot more going on in these equations, but this will suffice for the current level that you are at now. Next class, we'll move on to continue to talk about magnetic interactions, so you will want to make sure you understand what a magnetic field is, what a magnetic force is, and how to use the right hand rule in these situations. It's a pretty tough unit, but I appreciate you sticking around. Thanks for your attention. I'll see you in the next one.